interesting things happen in space. It is ever changing. When we finally think we've gotten a handle on things, something else happens to call all our theories into question. On this channel, we have already explored some pretty strange occurrences like asteroids with rings, a football-shaped planet, water on Mars, and we've even looked at what would happen if the Earth stopped spinning. And just when you think things can't get any weirder, now we hear that the sun is breaking apart. What does this mean, and how does it affect our planet? Join us in today's video as we discuss the mysteries of the sun and why it's supposedly falling apart. You may have heard that the sun is breaking, or rather that a portion of it came off and is headed for our planet. There are even some who claim that JWST captured the entire thing on camera. Well, we have to begin by telling you that these reports aren't exactly true. And while they make for amazing headlines, don't believe the hype, because what's happening to the sun is something quite different. To understand what's happening, we need to get familiar with some phenomena that happen on the sun's surface. Let's start by describing what's known as the solar cycle. A solar cycle is driven by the sun's magnetic field, and it refers to a period, usually of about 11 years, in which there is a dramatic increase in the sun's activity. This surge of activity is made evident by the increased frequency and intensity of sunspots visible on the star's surface. Solar cycles are difficult to predict as they don't quite follow a pattern. For example, a solar cycle could last anywhere from 8 to 14 years, and each solar cycle varies wildly in intensity and, as we are about to see, in activity. The current solar cycle started in December of 2019 and is expected to reach solar maximum by 2025. As we mentioned earlier, the level of activity on the solar surface is influenced by changes in the magnetic field of the sun. What typically happens is the polar magnetic fields of the sun diminish, reach zero, and then reappear with opposite polarity. In other words, the magnetic field of the sun flips around every 11 years, turning north into south and south into north. When this flipping of the magnetic poles occurs, its effects are felt throughout our entire solar system, and planets without a magnetosphere or magnetic shield feel the full impact of the flip. For example, in 2006, Venus was stripped of a large amount of oxygen because the sun released plasma accompanied by a magnetic field, also known as a coronal mass ejection, during an increase in solar activity. Earlier, we mentioned that a solar cycle is marked by an increase in the frequency and intensity of sunspots. But what exactly are sunspots? Sunspots are darker, colder patches of the sun's surface that form when the magnetic field of the sun is disturbed. Over the 11-year solar cycle, there are varying numbers of sunspots, with solar maximum marking the height of sunspot activity and solar minimum marking a pause in sunspots. This is why solar cycles are sometimes referred to as sunspot cycles. The amount of sunspots fluctuates from low to high and then back to low during a solar cycle. Over the course of the cycle, the positions of the sunspots also shift. At solar maximum, sunspots are found near mid-latitudes and shift to somewhere near the equator during solar minimum. At solar minimum, sunspots may also occasionally be completely invisible. Currently, the sun is in its 25th solar cycle on record. Another important feature appearing on the sun's surface are solar flares. Solar flares occur as intense eruptions of electromagnetic radiation, and along with sunspots, they emit high-energy plasma toward Earth. Think of a solar flare as a massive explosion that occurs on the sun when energy that has been trapped in magnetic fields is abruptly released. Scientists use the brightness of solar flares, measured in X-ray wavelength, in order to categorize them. And there are three main types that exist. Large-scale X-class flares are significant occurrences that have the potential to cause global radio blackouts as well as intense radiation storms in the high atmosphere. Medium-sized M-class flares typically result in brief radio blackouts that impact Earth's polar regions, while smaller C-class flares are minor and have little effect on Earth when compared to the X and M-class occurrences. Finally, to get us fully up to speed, the last thing we have to explain are solar prominences. These are loop-like, electrically charged plasma emitted from the sun from time to time, similar to how you might see coils of steam rising from a pot of boiling water. Solar prominences are actually quite common, in some cases building up and fizzling out over the course of a single day. However, some solar prominences are stable enough to persist on the sun's surface for several months and can extend hundreds of thousands of kilometers into space. The solar event that took place on February 2nd, you know, the one that had all the headlines exploding, was one of these regular solar prominences, which, as you now know, are a common occurrence on the sun. However, what was not regular about the solar prominence captured on February 2nd was the way the erupted plasma filament swirled around the polar region of the sun, forming what scientists are calling a vortex. The thing is, right now, even scientists don't exactly know what's going on. They've never before witnessed this swirling behavior of plasma, and currently they don't have a way to regularly image the sun's polar regions. But that is about to change very soon. Before we get into that, let's talk a little bit about how this February 2nd event was observed. And no, it wasn't JWST. This time it was NASA's Solar Dynamics Observatory, or SDO. Launched on February 11, 2010, SDO has been doing just what its name implies. It has been observing and studying solar activities, from their formation to how these activities affect weather and the planets in our solar system, giving us a basic idea of what goes on within our enigmatic star. By studying the sun's activities, SDO keeps us informed and ready to defend against any potential threats to our planet. It was SDO that observed the most recent solar prominence that formed what looked like a vortex. Currently, SDO travels in a geosynchronous orbit. From this plane, we can get a pretty consistent view of daily events happening on the sun, but we can't get a clear image of what's happening at its poles. Since this infamous solar prominence occurred at the sun's north pole, we still need more information to understand what exactly is responsible for creating the vortex. But we have a plan. By 2025, the European Space Agency's solar orbiter will be optimally positioned so as to take the first ever pictures of the sun's poles. It has been predicted that the sun will reach its next solar maximum by 2025. And you can be sure that ESA's solar orbiter will be there with front row seats and a camera capturing everything as it unfolds. As long as we're throwing out mentions of sunbound spacecraft, we would be remiss to leave out the Parker Solar Probe. The Parker Solar Probe launched in August of 2018 with one primary objective: get as close to the sun as possible. Why? To trace the flow of energy as it moves through the solar corona, and to better understand what accelerates the solar wind. According to NASA, the Parker Solar Probe was designed to fly through the birthplace of the highest energy solar particles. How can it get so close to the sun without melting? What is the bigger goal in studying the sun and its solar wind? We'll answer all these questions and more in our special video dedicated to the Parker Solar Probe, so why not click the bell icon so you don't miss it? Finally, let's take a look at the effects of solar prominences on our planet and our humanity. The solar eruption that occurred at the sun's north pole on February 2nd is not headed toward Earth, so we have little to worry about in regards to that event. However, in the past, heightened solar activity and solar eruptions have led to radio blackouts and the destruction of GPS, satellites, and entire power grids. In February of 2021, a solar flare destroyed 38 Starlink satellites, costing the company millions of dollars. And then let's not forget the famous solar storm of 1859, which caused the greatest geomagnetic disturbance ever seen. Commonly known as the Carrington event, it sparked fires in multiple telegraph stations, disabling newly established telegraph networks around the globe. If this event were to happen today in our modern digital era, it would cause a massive global communication breakdown. Do you think we'll ever get to the bottom of what caused this unusual solar vortex? Let us know in the comments.